Welcome to this screencast where I'm going to go over the second implementation of a list using a link structure instead of an array like we did last time. So here's our list interface again. We have two methods to get and set the thing at the index. We can find out the index of an object, see if it's in the list. We can say how many items are in the list. We can add an element to the end of the list. We can add an element into the middle of the list at the index, and we can remove an item from the list at an index. So we can grow and shrink our list. And in this implementation, instead of using an array, we're going to use nodes to store the data. So we have our linked list instead of our array list. They use nodes to store the data. There's no wasted space. If you recall, in the array implementation, we had to make the array bigger than the number of items because we didn't want to have to keep resizing the array. So in this case, we only have as many nodes as there are items in the list. We don't have to copy the items from one place to another. We just put them in the nodes and they'll take care of that. We don't have to copy, don't have to shift. It happens automatically. One of the problems, though, is that to get and set things, when we use an array, we get it just by grabbing that item. Since we're using a link structure, we actually have to traverse to the place. So that means our get and sets are slower. And because we're using a link structure, it's more complicated than the array list, which is just I have an array and I have size. So this is more complicated. There are more cases to deal with when you're adding or removing and all sorts of things. We'll see that very quickly. But it is a very nice data structure, and learning how to manipulate nodes is a very valuable thing. We're going to use them all over the place for the rest of our data structures, our trees, our hash maps, all sorts of things, stacks, queues. We'll use these nodes. So what is our node implementation? We have a private node head. So it's not an E, it's not an array of E's, it's a node that stores E's. And we have the head, that's the beginning of our list, and we keep track of the size. We could count them each time, but why do we want to count them? If we remember the size, we can easily just return the size. So what is a node? It's a private inner class. So it's inside the linked list. The outside world does not know anything about nodes. They don't want to know anything about nodes. It's our job to keep track of the nodes. Node has a thing of type E to store the item that we're holding, and it has a pointer to the next node in the list. So that's how we could start with head, and then head.next will point to the next thing, and we can traverse down. We can also add a second pointer if we want a doubly linked list that points to the previous. So you can say, I can go to the next one, or I can go to the previous one. And this is very handy when you want to traverse a list and go in both directions. Because if I can only go to the next, that means I got to start at head again and again and again. We'll not be talking about the doubly linked implementation for this one. We're going to just do the singly linked implementation. So we have that private inner class, added a little complexity, but now we want to initialize our linked list. So what do we do? Well, when we have our constructor, we need to initialize our member variables. We have two of them. What does an empty linked list look like? Well, its head is null, saying there's nothing there. I don't have anything. I'm not storing anything. And what is its size? The size is, of course, 0. So I have nothing. I don't have anything in it. And head is null. So there's nothing there. So now let's go and talk. We have our list. We've done our thing. So now I've got my list. Its size is 2. I want to get the item at index. So what's the first thing we need to do? Whenever we have an index, we need to check it because we don't trust the people using our program to give us 100% good data. So we need to check the index. So again, if the index is less than 0, they give me negative. I don't like them. And if it's greater than or equal to size, because I can't access the thing at size, I throw an index out of bounds exception. So then I return the item at index. Well, I can't just get to the thing at 1. I've got to start at the only thing I have a hold of. I have head. So I start at head. I move index steps down the list, and then I return the data of the node. I don't return the node. I've got to return the E stored in the node. So let's start at head. We create a temp as a type node. So it points to the head. We then move index steps forward with a for loop, starting at 0, going to less than I is less than index. How do I move temp forward? I say temp equals temp.next. So what that will do is it will move temp to point to temp.next. And now it's pointing at the first thing. And I do that until I get to the index, in this case 1. And I say I need to return the thing, not at temp, because temp is a node. I need to return temp.data. So I return the E stored in my node. Remember the return types, very important. We don't return nodes. Nodes, the outside world doesn't know anything about nodes. We, as the implementers of our linked list, know about nodes. And the big O of this method is big O of n because I have to go down the list. I have to start at the head and go 0, 1, 2, 3, 4, 5 till I get to the index, and then I can return the data there. So that potentially is I have to go through the whole thing, so that's big O of n. Remember in the array list, it was big O of 1 because I just went and said data subindex. So now, what's the set look like? Again, we need to check the index. We remember the old value because set returns what was in the list and changes it. And then I set the value at index and return the old value. So again, check the index. You're going to love this. You're going to know this by heart. Then I remember the old value. Well, I got to get to the old value. So again, start at head, move index steps, remember the old value, set the value in the index. So we start at head, we go forward, and now we're staring at the thing we want. Now I got to remember the old value, so I create a local variable, retval or old value or whatever you want to call it. Store the E. Again, I don't want the node, I want the data. And I then set the data, so it's temp.data equals the entry that you're given, and then I return the old value, so I return retval. And I'm done, and the big O of this, again, is big O of n because I have to move my temp pointer down through the list to get to the bottom. Index of, same problem, we got to search through each item in the list, checking to see whether it is O. And then if it is, we return the index. If it's not, we get to the end of the list. We've looked at everything. We return a -1. So we, again, create our temp. So we're going to use it to search through the list. We're going to go from 0 to size because we want to go all the way through. If O is in the list, we return the index. So if temp.data equals O, so we're saying the thing at temp's data is equal to the thing we're looking for, we can return I because that's the index. If we get all the way to the end, oh, then we need to increment because we didn't find it. So we need to say temp.next. The temp equals temp.next, so we move temp. Now we can check this one, and then we're going to do that size times. And if we get to the end, then we didn't find O in our list, so we return -1, indicating, sorry, we didn't find it. The big O of this is, of course, big O of n because we have to search the entire list to see if it's there. If we find it, it returns, but if it's not there, we got to search the entire list, big O of n. So then we've got index, so now we're going to start with how many items. So the size, again, we could count them. It's easy to count the linked list because you just go until you fall off the end and temp is null and you keep track. But why do we need to do that if we could remember the size? So we remember the size and we return size, big O of 1. And that's why we do it instead of counting, because it would be silly to say, oh, what's the size? I count to 3. What's the size? I count to 3 again. What's the size? I count to 3 again. If you remembered the size, you would just have to say it's 3. Okay, so now we want to add an item to the end of the list. This is the simple add that only takes one parameter. Now, in the linked list, there's a special case. What if the list is empty? We need to update head because head is at the end of the list in this one case. So we need to have the special cases if size is 0 or if head is null, but we have an empty list. So we need, if head is null or size is equal 0, then we have an empty list and we need to add the entry at the head instead of at the end because the head is the end in this case. So we say head equals new node entry null. And this is a constructor on node that I didn't show you, but it's going to take you the value I'm passing in, and set the next pointer. So I can construct my node in just one constructor. I could do it with a default constructor and then say head.data equals entry, head.next equals null, but I can do that in one constructor and make my life easier when I implement this. But again, that adds complexity to my node class, because now I have to have a constructor that takes 2 parameters and not just the default one, but that's okay. So now I've got new node. I need to increment, so I created it. I need to increment the size. So now I have 1 item in it, and then I return true. So this is done. Now I should probably put the size and the return inside the if, because in the next slide you'll see that we have the else. But we could always do that, increment the size and return true at the very end of the method, whether or not we just dealt with the head or at the end. So now it's not an empty list, so we want to add to the end of the list. So what do we need to do? We got to get to the end of the list. So we start at the head, move size -1 times. So we want to be pointing to the last item in the list, because we got to update its next pointer. We can't fall off the end and be pointing at null and assign it, so we got to move 1 short of the end. So we started ahead with our temp. We move to size -1 so that we'll be pointing at bar in this case. So we move forward, and now we need to create a node to hold the new entry. So we say temp.next equals new node entry null. That's going to, again, set that last pointer's next is going to be null, so it says we're at the end. And temp.next was null, but now it's equal to this new node. Increment the size, return true. And again, we can move that size ++ and return true out of the else block. Big O of n squared again, or excuse me, n, because we move we have to start at the beginning and move all the way to the end of the list. Nothing we can do with the link structure, because we only have the beginning and we can get to the end. Now, there is a shortcut that makes the add at end a big O of 1 operation if we keep track of the end of the list, or the tail of the list, the end of the list, because we're adding at the end, or they're adding at the tail. So if we keep track of the tail, then we can just add at the tail. And again, we have 2 special cases. We have to add another tail pointer, because we need to keep track of the head. We need to keep track of the tail, so we add another pointer into our linked list. Again, more complexity. The first case is we have an empty list. Size 0, head, and tail are both null. So if head is null, head equals new node entry null, and then we have to assign tail to be head, because that is the last item in the list. We increment the size, we return true. And now the other case is there is a list, but tail is actually pointing to the last thing. So we now want to add to tail, right? We want to add to the end of the list. So tail.next equals new node entry, creating the new node. We need to now, tail's not pointing at the end of the list anymore, so we need to update tail. We increment the size, return true. So that's a big O of 1 operation, because tail is always at the end of the list. We don't have to move to the end. So that's a big improvement in our performance of the add at the end. So that's the more efficient add at the end. So now if we want to add at the middle, or index somewhere in the middle of the list, again, because we're dealing with index, we got to check the index. We need to move to 1 before the index. Again, we can't set the thing. We got to set temps next. So we start at the beginning. Again, special case. If the index is 0, we need to update head, because we're inserting at zeros. We're inserting at the beginning. We need to have head point to this new thing. So if it's update to head, so we say head equals new node entry, and then we pass it the value of head. So remember, we're going to do this sort of as you imagine, it's 2 steps. We create a new node whose data is entry, and whose next pointer points to what head does. So we create the new node, points to what head is, and then we reassign head to that node. And so now we've shifted everything down. We didn't have to shift anything because the links point to things. They all shift magically. We increment the size, and since this is the one that doesn't return anything, we're done. So that's the special case of if I'm inserting at the beginning. If index is 0, I am inserting a head. Else, I need to move to index -1, so I start at head, go forward, and then I got to say temp next equals new node entry, temp next, so I'm going to create a new node that points to temps next, so that will be Baz, and then I assign temp next to point to the node, and that will shove that in there, and there we go. We've inserted it in the right place. We increment the size. Again, we can move that increment of the size to the end of the method because we'll do it both if it's index 0 or anywhere else. For efficiency, the big O of this method, again, because I have to traverse down, is n, because I got to go down to the size -1 or the index -1 guy and then add after. So that's the last, and then the last method we were talking about is to remove. So if I want to remove something, again, we have an index. Always, if you have an index, you got to check it. So we check to see that it's valid. If not, throw an index out of bounds exception. The thing is we need to remember the value that we're removing, shift the items, and then decrement the size and then return the removed value. So how do we remember the old value? Well, we got to get there. So we're going to create, the first thing is if index is 0, we need to update head, right? We're going to remove the thing at 0, and then, so we need to update head, because head always points to the beginning. If we're removing the first thing, head needs to point to the new first thing. So if index is 0, remember the old value, which is head.data. Again, we're remembering the E, not the node. We need to shift the items. Well, to shift the items, that's really easy. I can just move head. Head equals head.next. So that moves head. Foo is not pointed to by head, so the beginning of the list is now 0. Foo is still there, but will be garbage collected because no one is pointing to it or referring to it, so it gets garbage collected and disappears. We got to remember to decrement the size because we now only have 3 things in the list, and we return the removed value. We return old val. So that's the case where we had to update head because we're removing the first thing, or the thing at index 0. Else, we need to move our pointer down to where the thing we're removing, right before the thing we're moving, and then we shift the items. And then, so I need to move to index -1. Remember that value. So I start at the head, I go to index -1. So in this case, I'm going to remove bar from the list. So I remember the value, which is temp.next data, right? So I got to remember bar because it's going to be removed. And then to shift the things, all I need to update is temp.next. So if temp.next equals temp.next.next, then I jump over bar. And again, bar is no longer pointed to in this list. So it will be garbage collected sometime later, and it's going to be gone. And so that will shift Baz and all the rest of them up 1. I got to decrement the size. I then return the old value, and we're done. And the big O of this again is n, because I got to move down to index -1. So that's big O of n, and I removed it. So what's the comparison between the array list and the linked list? Is basically the same, except for the linked list is slower on get and set. They're the same on add. So basically they're the same. If you do that special add at n where you remember tail, then the linked list is big O of 1. If you don't, then it's big O of n. And so the linked list is slower in the get, set, and potentially add. Otherwise, it's the same performance as the array list. So some people might ask, why would you ever use a linked list? I don't know why. It's a good implementation. Maybe if you're worried about having wasted space in your, memory is limited, you might try a linked list because there's less wasted space in a linked list. But for an implementation, it's good for you to practice manipulating nodes and dealing with shifting things around, because we're going to be dealing with trees and queues and stacks and things where we'll have linked implementations. Thank you for your attention.